All right, we're getting into a new chapter that deals with the acids and bases we talked about in the previous chapter. Only this is a much more practical application for it all. And we call this section titrations. Now, titration is an analysis. Now, I put a video on there that shows an example of an acid-base titration. In fact, the one that I'm going to do an example of is the type of titration that I'm going to be doing, that they're talking about. So, this is the workhorse of chemistry. This is the analysis that is done by a lot of labs for various reasons. My best friend in college became the top toxicologist for the state of Illinois crime lab. He also dealt with chemical analysis of drugs that have been confiscated, using titrations to figure out the purity of the substance and a whole lot more. This is big time stuff. Now, what we are going to do is we're going to look at the breakdown of it and how all these numbers come into play and how we deal with the neutralization reactions and all that. So this is probably going to be a pretty long video with all the stuff that we have to do. So let's get right into it. When we titrate something, we either going to have, we're going to start off with a beaker of a strong acid solution. In the burette, which is that long pipe or tube that they showed in the video, you're going to have a strong base. Now we're going to take known quantities, so what we are going to do is we're going to have equal concentrations of acid and base. Now when we get to the very end, that'll change a bit, but we're going to get into how the calculations are determined for this. And so what we're going to do, see, I have the example here. What we're going to do is we're going to take 120 milliliter solution in a beaker, and we're going to titrate it with, in the beaker is 0.800 molar HCl. So it's a fairly potent amount of hydrochloric acid that we are going to be titrating. And we're going to add to it bit by bit milliliters of 0.800 molar NaOH. Like I said, the acid-base concentrations are going to start out being the same. So we're going to start off with no base being added, and then we're going to add 20 milliliters to the beaker, then 60, then 80. Actually what's going to happen, I'm going to add 20 to this, and I'm going to add 40 more, which gives a total of 60, then 20 more to make 100, make 80, 20 more for 100, 20 more for 120, 20 more for 140, and then 20 more for 160. And we're going to calculate the pH at each point where they come up with these values. Now, when they do titrations, they use something called an indicator to help you kind of let you know that you're really close to the point. Now, the pH meters we have aren't very good. We may try and get this done before the school year's out. We'll have to see how things go. The indicator will change pH to let you know that you're getting pretty close to what we call the equivalence point, the point in which the amount of acid and base are identical. And that's going to give you a pH of 7. So we need a calculation process. Now I have also included a sheet that looks something like this without any numbers in it. I'm going to be filling in these numbers to let you know how this is all calculated. I'm also going to have 2 calculation sheets showing the neutralization reaction. Now this is a neutralization reaction. And the neutralization reaction is simply showing how acid and bases neutralize each other. When they have equal quantities, they become sodium chloride, which has no acidic or basic qualities to it. It's neutral, and water, of course, which is neutral. So when you start with the HCl and we begin to neutralize the acid slowly but surely until we get to the point where we have equal number of moles of each. So what we are going to be doing is at each point in the titration, we're going to look at the number of moles we have. Well, first of all, for this particular problem, we have 120 milliliters, which is 0.12 liters or 0.120 liters. Okay? And the number of moles, we can take 0.120 liters and multiply by 0.800 moles per liter. Well, I'm going to write moles per liter even though it says capital M on that. The liters are going to cancel out, and this is going to give us 0.0960 moles. Okay? Now, that is the number of liters we have in the solution of just acid. And I'll just put H positive because it's a strong acid, so it's giving off hydrogen ions. And the pH, of course, is going to be determined by how much H positive we have. And the number of moles that we have at the onset is 0.0960. So in this chart, I have written 0.12 liters, and I've drawn this arrow, which means that quantity stays the same all the way down. And we found 0.096 moles for the acid. That's going to stay always same all the way down. Then this is the volume of the base based upon what the problem or the example gave us. And then we're going to calculate the moles and fill in the rest of the blanks here. Now, the first row is not truly a titration because we haven't added anything to it. But in theory, this is what it's going to look like as you go through all these columns. You have your moles of base that you can put here. Your total volume is VA plus VB. That's how much the beaker is going to have in it. The moles of excess, these two moles are going to react together. Now, since there's no base here, it's not going to take off into 0.096. So we have an excess of 0.096 moles of hydrogen ions. And then the concentration, which we had from the very beginning, is simply the moles of excess divided by the total volume, which of course is 0.800 molar of the H positive. Since we had only acid in it, and it's a strong acid, hydrochloric acid, it's going to be H positive. So the pH is the negative log of that, which is like 0.0965 or something like that. But the deal is, when we do pHs, and anytime we do any work with pHs for me, I want 2 decimal places for all my answers. Even when it's 7, exactly 7, you're going to put 7.00, okay? Just for consistency's sake all the way through. So, what we're going to do next to start filling out this chart is we're going to take the first scenario here. Now, I'm going to put the HCl stuff here, and that's, we said again, is 0.800 moles. Now, for the sodium hydroxide in this problem, any minute now, in this problem, the first one is 20 milliliters. I'll stop before going back and forth here. But we're using these numbers, so I'm not going to keep that handy as I go through this. So we have 0.02 liters times 0.8 moles per liter. And that's going to give us 0.016 moles of my sodium hydroxide. So I have 0.02 liters and 0.016 moles I'm going to put into this chart. And I'm going to use red from now on to show that's different from all the other stuff that we've done here. So for the volume base, we already figured out, I already had put down 0.02 for this. I've already given you the number of liters for each one of those. It's just basic changing over to the other label. We said that this is 0.096 moles. Now, so here's the thing about neutralization reactions. When you have equal quantities, they equally knock each other out. But like we've done with ice problems before, if you have 0.800 moles here and 0.016 moles here, actually it's this is 0.096 moles. Okay, that's what we started with. And when we multiply these together, right, that should have been 0.096 right there. I have that of the acid and this of the base, and since this is smaller, we're going to lose 0.016 from both sides. And we get 0.08 moles of hydrogen ions, and we got nothing left at the base. There's no base in the solution when these two have completely reacted. So, I'm going to put point 0.08. Okay? Now, the moles, I'm sorry, that's the moles of excess of H positive. Now, the total volume is 0.12 plus 0.02, which is 0.14 liters of the total volume. The concentration then is going to be the 0.08 moles divided by the 0.14 liters, which will give us moles per liter. And this is going to give us 0.571 moles per liter of H positive. I take negative log of that, and I get 0.24. So we've added 20 milliliters, and the pH went up by 0.24 because you're adding a base, and base is higher pH than acid, so we expect it to increase. Okay? So now, we go to 0.06 liters for the reaction. So we got 0.06 liters times 0.8 moles per liter. And this gives us 0.048 moles of base. And again, we still have the 0.096 of the moles here. And since we have less of this and this, we're going to subtract 0.048 for this, because that is going to eat up 0.048 of this, to leave you 0.048 moles of the H positive.